All right, everybody, welcome to Code Astro Day 4, second to last day of lessons. Super excited. Today we're going to cover testing. We're going to spend the first, testing is sort of like 2 lessons in one. We're going to talk first about how to write good tests and what to test for. And then in the second half of the lesson, we're going to talk about tools for testing and automating your tests. So just as a reminder, as always, this is our anonymous feedback forum. We've been getting some really great feedback so far throughout the workshop. We want to encourage you to keep using this. And then all of the different ways to ask questions. You should ask questions in the chat box on Zoom. You can ask questions on Piazza, and remember there's this anonymous option on Piazza. And on Discord, we recommend you use Discord to communicate with fellow participants. You can also ask questions there. And as a reminder, we're going to be monitoring these mediums before, during, and after lectures. So you can ask anytime you want, and someone will answer your question. And just one more reminder about how to group work. I will, again, try to remind you about these things today, but please feel free to spend the first 10 to 15% of the time thinking. You don't need to jump into talking with other people in your group right away. And then also assign roles and switch your roles often. So far, we've been talking about pair programming a lot. So we've talked about drivers and navigators. For today, the driver, if you need a way to assign a driver and a navigator first, we recommend that the driver should be the first person with the farthest birthday away from today. The navigator should be the person with the closest birthday to now. And then especially during the optional lessons later, we'll also need a reporter. So that'll be a new role of a person responsible for taking notes and reporting results. So just to remind you about the overall goals of the workshop, by the end of the workshop, you'll be able to use the language of software development, develop and release an open source astronomy package, and write code that follows best practices of software development. Today specifically, you're going to be able to actively avoid discriminatory behavior when coding, and then write tests based on anticipated use cases of your code. Today's the last day of the project prep. Tomorrow, the first thing will be, you'll be presenting your projects if you so choose. So the project tasks for today are to add tests to your repository and try to debug your code so all the tests pass. And then also all of the tasks from yesterday, documenting your code with doc strings and Sphinx. Optionally, you can put your documentation online, get it set up with Read the Docs. We also want you to make sure that you package and upload your code to PyPy. Remember, tomorrow you're going to switch your project with another group, and you'll get to see someone else try to install and run your package, go through any tutorials you have or something like that. So. So as an example for our fictional project, we'll write doc strings for a couple core classes and functions and add a tutorial to our README. We'll then write unit tests that evaluate the performance of key functions and end-to-end tests to make sure that the whole package is working. We'll put our code on PyPy and try pip installing it on each of our machines to work through installation problems. Today we've got 2 optional lessons in the same place here as always and on Zoom with the same Zoom link. 1 to 2 immediately after lunch, we've got an optional lesson about preparing for future observatories. This is sort of more like a focus group for the future of Code Astro. We're really curious about y'all's thoughts about what you want, how you see Code Astro changing in the future, if there are other topics that you'd like us to cover with the same format. It's really important to us that we have a good group of people there. We really want your feedback, and we want to be able to show funders, for example, that there are specific things that people in our workshops are looking for. So we'd really love for you to come to that workshop. That would help us a lot. What?
1 or 2 to 2 to 3 or 1 to 2?
I thought it was 1 to 2.
I was going to say on the calendar on the website it says 2 to 3
on
the
dang. Okay.
workshop schedule.
Okay. We'll let you know. We'll say on Discord. Okay, let's assume it's 2 to 3. What did we tell?
I'm trying to find the calendar.
Okay. Sounds good. Right, because I invited them on the calendar. Hold on, this is important. Let me check. Okay, 2 to 3. On the calendar is 2 to 3. Okay, so not immediately after lunch. 2 to 3 is preparing for future observatories. And then 4 to 5 is profiling. So this is figuring out which parts of your code are taking the most time so that you can focus on speeding up your code. And that'll also be here. All right, so let's talk briefly about the project presentations tomorrow. So we've got the first 90 minutes of the project presentation slot is going to be time for you all to optionally present to the whole conference. You're going to get 4 minutes each, and we're going to time you for 4 minutes just to make sure we can get through everybody that wants to present. I said this, I think, at the beginning of the week, but just a reminder, you can present however you like. You can you can show off your docs and the actual code itself. You can walk through a tutorial or show yourself actually using the code, do a little demo. You can also you could do a presentation if you want, with slides talking about the motivation for your project. It's really, the world is your oyster, however you want to show off your project to the whole conference. And then for the next 30 minutes, you're going to swap projects with another group, and you'll try installing and actually running each other's code. So the sign up is here, it's live. So if you want to sign up to present, go to that Google Doc and just add your group's name. Also note that you don't have to, not everybody in your group has to participate in the presentation. So for example, if one person really doesn't want to get up in front of everyone and present, but 2 people do, that's totally fine. Another thing that we want to ask you to do is to add your project to the Code Astro database. And we're not going to publish your code anywhere without your consent or something like that. It's basically just for us to track the impact of the workshop. So we can write in future funding proposals that this number of open source packages came out of the Code Astro workshop. And very importantly, I know getting to day 4, there's a lot of stuff. People sometimes start to feel stressed and overwhelmed about getting the project done today. Don't sell yourself short. You can do this, and you all belong here. The other thing that we're doing tomorrow is a panel on industry software development. So we're going to talk both about how do you transition from academia to industry, and then how industry looks different from academia, both in terms of daily life and then what the actual work looks like, how software practices differ in academia and industry. So we've got 4 folks, including me and Jason, Chai, who's a remote TA online, and then Daniel, who's somewhere around here. Where are you? Daniel's in the back there. So all of us have experience both in academia and industry, and we're going to share our experiences with you. So please bring questions. I think Jason has a couple of questions to get the panel started, but then most of the time will just be answering whatever y'all want to know. Oh, and I should say too, that's the first thing tomorrow. So that'll start at 9 a.m. tomorrow, and then we'll do the project presentations 10 to noon. Also, one last reminder, in-person folks, we've got a couple of van pools going back on Friday. So if you already signed up for a van pool, just check that your information is up to date. And if you haven't signed up, if you want to be in a van pool, please feel free to sign up. And as a reminder, as always, just make sure you have the latest version of the Code Astro repository. So you can either do this from the command line, stash your changes, and then pull down the changes from main, and then apply your changes. You can also just sync here, especially if you have a forked version. All right, I think that's it. So let's get started with testing. All right. Take a minute to appreciate the meme. You all liked Pip Girl a lot better than this one. It's funny which memes resonate with people different years. All right. So just as a quick note, I'm going to use Piazza polling in this lesson. So please open up Piazza so you're ready to answer. All right, so the overall goals of this lesson are that by the end, you'll be able to explain the difference between end-to-end and unit tests, understand why continuous integration systems aid collaborative development, and also write tests based on anticipated use cases of your code. So let's start off with some motivation about why we might test code. Testing in general is crucial not only to a code's accuracy, but also to its flexibility. So we all write tests to some extent. Generally, whenever you write code, you'll like run it and see that it like produces an output that you expect. But I think the difference between like how sort of like default software development is done in astronomy and like sort of professional level software development is the amount of time and effort spent developing tests. So I say here that excellent developers spend most of their time thinking about and writing tests. Writing excellent tests requires a lot of creativity because you are not just testing like, you know, the code does this particular thing, but you want to anticipate all the different ways that users might use your code and potentially break your code. So if you're like trying to be a really excellent developer, trying to anticipate that as many use cases as possible is really important. Testing also ensures that your code maintains the same behavior over time. So if you have a test suite, say you have like 50 tests that you wrote, and somebody, you know, that you've never worked with before makes a pull request to main, you can run this test suite and ensure that this new functionality that somebody else contributed didn't break anything existing in your code already. So this is really nice to like, maintain that ensure your code maintains this behavior. So one of our goals for you today is to get in the habit of writing extensive and thorough tests. All right, so now let's talk about different types of tests. So one of the goals for this lesson is for you to understand the difference between unit tests and end-to-end tests. Unit tests evaluate the correctness of individual elements of your code. So you can think about this as testing on a very small scale. End-to-end tests, on the other hand, are going to test on a very large scale. So a unit is like the smallest testable part of any software. So this might be like testing an individual function, for example. Unit tests generally have few inputs and outputs. Let's talk about some examples of what you might test for unit tests. You might test that the output of a function is correct for every different possible type of input. So let's say you write a function that like sums two Python objects, and it works for several different types of Python objects. So you might want to test that it works for strings and arrays and floats, for example. It's really important to include edge cases. So for example, if your code operates on integers, make sure you test the input 0. Sometimes 0 behaves strangely. If your code operates on strings, try testing weird strings. So for example, pi mense, since there might be like, if you have like, you know, non-ASCII characters. People sometimes ask, how do you test plotting code? Generally, we recommend that you just test that plotting code doesn't fail. It's really hard to like evaluate whether a plotting code like, you know, made the correct plot automatically. So generally, like in Orbitize, for example, we just have like when we're testing plotting code, we just run through the plotting code and test that it makes it to the end. Importantly, you don't need to test on inputs that are not allowed by your documentation. So anything that isn't like actually strictly a part of your code, that your code isn't defined to do, is fine to leave out of your tests. You want to test the actual behavior, the intended behavior of your code. You don't need to test non-included cases. So for example, if your doc string says that my int is an integer, you don't need to test a float input. That's like if a user puts in a float there, it's fine to say this is an undefined behavior. So here's an example of a unit test in Orbitize. I'm going to take you through what this test is doing and then ask you a couple questions about it. So this is test RIDEC to set PA. So you can think about this like the RIDEC to set PA function in Orbitize converts Cartesian coordinates to polar coordinates, so x, y to separation and position angle. So what we're doing here is inputting a set of right ascension and declination values, so like x and y values. And you can see that each one of these x and y values are in each of the 4 quadrants. So we've got 1, 1, -1, 1, -1, -1, and 1, -1. Then I'm putting in the expected outputs, the expected position angles, and the expected separations. I've also got in here the expected position angles if we include the mod 180 keyword. So if we're modding by 180 degrees. So this is a keyword in the RA-Dec to set PA function, an optional keyword. So I want to check that that keyword works as well. So defining the inputs, defining the expected outputs, and then I actually run the code. So here I'm running it without this mod 180 function. And then here I run it with the mod 180 function. And then finally, I have these series of assert statements to make sure that the test actually produces the correct output. So I'm asserting that this output is equal to the expected output. I'm also using this pytest.approx function. And the reason for that is because if you test that two floating point numbers are exactly equal, you'll often get failures because of numerical precision differences. So pytest.approx allows you to say that these two are equal to within some absolute tolerance. All right, so now a Piazza question. So I want to ask you, what's an edge case we should test for the RA-Dec to set PA function? So I'll give you 5 minutes to think about it and write your test on Piazza. All right. Yeah, see some really great answers. So testing invalid RA or DEC inputs, numbers that couldn't be RA-Dec. So I might think about things like NaN values or infinity. I really like the large angles, so maybe negative angles or angles that are larger than 360 degrees. Radians is a really interesting, very interesting idea. So here we're, I guess, so it's interesting. So the PA is the output here, since we're going from X and Y to separation and position angle. So the out of range of 360 might be really good for the opposite if we're going from separation and position angle to right ascension and declination. 0, 0 is a really good input. I also really like the empty list as a great suggestion. So what if you don't have any right ascensions and declinations? What does it do in that case? So invalid variable formats, if a user inputs a string rather than a float. Keep in mind that you didn't see the actual doc string of this function, but remember that if this isn't allowed by the doc string, it's totally fine to not test for that. This is really good too for RA test 0 to 24 to see if the behavior is the same. So making sure you test across the full range of inputs. Awesome. Great job, y'all. All right, let's keep going. All right, so we talked about unit tests. Let's now talk about end-to-end tests. So remember, unit tests test the smallest bits of code. End-to-end tests, on the other hand, are going to evaluate a code's ability to perform its intended functions. So from the start to the end, you want to see that the way that your user actually is going to interact with your code works from start to finish. So you want to test the overall performance and accuracy of the code's main functions. And like I said, the way that users will interact with the code works. I have a note here that this is not always amenable to continuous integration. I'm going to talk more about continuous integration in a couple slides. This is the practice of automatically triggering a suite of tests every time someone makes a change to your code. So what I mean here that it's not always amenable to continuous integration is, for example, if your code takes a long time to run, it might be really hard to run full end-to-end tests every time someone makes a change to your code. So this is an example of a fast-running end-to-end test in Orbitize that we include in our actual continuous integration suite. So here we're testing that basically if somebody sets up all of the Orbitize functions the way that we expect, and they actually run an orbit fit, that they get an answer that's consistent with a published independent implementation of the same algorithm. So we start by initializing all of the objects that Orbitize needs in order to run a fit. And then here's where we actually like run Orbitize. So we run the sampler, we ask it to give us 1,000 orbits that it accepts at the very end. We're also running in parallel here, so we have 4 cores. And then what we're doing down here is checking the output values of the orbit fit. We're getting the median value here for each of these different orbital elements. And then we have the expected values. And then here at the bottom, we're using the same pytest.approx statement to make sure that the output values are within 20% of our expectation. Okay, so next Piazza poll. What's an example of an end-to-end test relevant for your project? Could someone in the back close the door? I think they're doing a fire alarm test in the dorms over there. So it's not going to affect us, but people are going to be like walking around out there. All right, so I'll give you 5 minutes. Post on Piazza an example of a relevant end-to-end test for your project. All right, I'm seeing some really great answers on Piazza. So like testing a full run on other operating systems, that's a really nice example of an end-to-end test. But a large enough subset of model outputs is statistically similar to that test's recorded outputs. Yeah, that's really great. Like comparing to an independent implementation is a really nice way to do an end-to-end test. So for a known data set, verify that our optimal color bar scalar produces the expected normalization. Yep, so like that the whole way that your user is going to use your code works exactly as you expect. Read through, I encourage you to read through some others. I'll like move on just to save time, but you all did a really great job here. All right, so the next thing I want to do is just show you what the test suite in Orbitize looks like. So you just have some examples. I also want to show you the structure of the test suite. So in Orbitize, we go to tests here. So this is in the level of the root directory. So our code files that comprise the actual package itself live in this directory here. But if we go one level up to tests, so we've got our unit tests are in the root of this repository. You can see we've got all of these Python files that start with test_.py. This is a format that we need for PyTest, which is a tool we're going to talk about in the second half. So here's an example. We've got a couple of these small little functions. So this is testing the basic functionality of a particular method that we have. So you can see here we're just like, we're reading an input file. We're then setting up this Orbitize system object. And we're testing that compute model, which is the method that we're trying to test, produces a model that has the correct shape in a couple of different circumstances. So we've got several different tests inside of these test_.py files, and they all sort of have a very similar structure of like setting up some expectation and then using one of these assert statements to check that everything runs correctly. In general, the behavior you want is for your test to fail if you don't get your expectation. So you want the test to not work. That's why assert statements are really handy in testing, because they assert that something is true, and if it gets false instead, it stops the runtime of the code. We also have, if we go back, a suite of end-to-end tests here. So these are where we're running like full orbit fits that we can compare to published fits in the literature. These take a little bit longer, so they're not run automatically every time someone makes a change to the code, but we have them there and we'll run them like periodically, especially before a major new version release, to make sure that the behavior of the code is consistent overall. All right. So now we've got a 45-minute think pair activity. So the idea of this is that you're going to get some practice writing tests for a piece of code that you've never seen before. So think pair, meaning that you're going to get 30 minutes to work through this on your own, give it an honest try by yourself, and then 15 minutes to compare with a partner. Online, you can just join any other breakout room where there's one other person, or you can just join by yourself and hopefully another person will come. In person, you can talk to just the person next to you. So I've got a link here. I think Yeah, okay. So just to give you a sense of why we're doing this, the purpose of this is to practice writing unit tests and end-to-end tests for an existing piece of code. This is sort of a different use case than what you're going to be doing for your own packages where you know the code really well. In this case, you're writing tests in order to like sort of understand the functionality of the code. The process, we want you to spend 30 minutes giving an honest try, and then discuss your solutions with another person. And then at the end, both you and your partner should have filled in the 2 unit tests and the 1 end-to-end test. There's lots of different solutions to this, so don't feel like your solutions need to be exactly the same. And I'll walk through my solution at the very end. So yeah, let me know if you have trouble finding this. It should be in the normal day 4. You should be able to find these slides in the day 4 folder, but let me know if you have trouble. All right, so I'll start the timer for 30 minutes and I'll let you know when it's time to start talking to a partner. All right, if you haven't started talking to a partner, you'll now have 15 minutes to share with the people around you and figure out your solutions together. I'm seeing a lot of kind of confused faces, which I think is good. This is also secretly an exercise in understanding object-oriented code, so it's definitely struggle through it. Keep going. All right, so you have 15 minutes to talk to other people about it starting now. All right, let's look at some of the solutions. So can I first do a little poll of the room? Like, how did you feel about this? Thumbs up if you felt like it was great, thumbs to the side, or thumbs down? All right, thanks. Yeah, so in general, like one of the most common things that you all wrote in your application forms that was confusing about the diagnostic was classes and object-oriented programming. So again, part of the goal of this was to give you some hands-on practice with object-oriented programming. So let me go through, I'm briefly going to talk about what this code does, and then talk about the unit tests and end-to-end tests that I ended up writing, and then we'll take a little break. Okay, so this takes in some time, a one-day array of times and a one-day array of data. Then it fits a line, and it uses NumPy polyfit to do this. The way that it like stores the results of this fitting is it creates this self.lin coefficients and self.linear residuals attributes of this class, and then it stores them there. It also does this to, it fits a quadratic in the same way, and then it creates these new attributes, quad coefficients and quadratic residuals. Then it plots the best fit. It makes this plot. It adds a scatter plot of the actual data. And then if the linear residuals are less than the quadratic residual, the sum of the linear residuals is less than the quadratic residuals, it then plots the linear residuals, and then otherwise it plots the quadratic fit. Sorry. If the linear residuals are less, it plots the linear fit. If the quadratic residuals are less, it plots the quadratic fit. So the first question I asked was how would a user interact with this code? They might just want to fit a line or just fit the quadratic function, or they might want to do the full comparison and plot the best fit at the end. Oh, sorry, do we not? Okay, thanks. So what are some edge cases? Some edge cases that I wrote down were having 0 data points in the input, so an array of length 0, having only 1 data point, having where all data points are 0, or maybe the data points perfectly define a vertical line, which is going to have an undefined slope. And there's lots and lots more edge cases here. All right, so here's the first unit test that I filled in. So the first thing we wanted to do was test that the least squares behavior, check the fitted values of M and B with an analytical solution, and check that the residuals are what you expect for a perfectly linear data set. So the first thing we did was make a time series. So we set the values of M and B. We then generate some times and some data points. The next thing we do is instantiate the compare fitter class. And then we actually run the compare fitter fit line function. And then we access these linear coefficients, the 0th value of this array and the first value of this array. And those will be the fitted values of M and B. And then also access the linear residuals. Then finally, what we're doing is assert that the fitted value of B is approximately equal to this analytic input value of B, and same for the fitted value of M. And I also test that the linear residuals are approximately 0, since this is a perfect line. The second unit test, I imagine that it made a lot of sense for folks to also do a very similar thing for the quadratic, which is totally fine and what is expected. I also want to show you in the solution how you might go about testing that a particular type of error is raised. So say for the empty array, right now this code actually doesn't raise its own error. It's going to raise an internal type error. But if that's the behavior that we want, we can actually check that the correct type of error was raised. So we're going to instantiate the compare fitter object with this empty times and empty data. And then we use this with pytest.raises, actually do the fit line code. So that's going to fail if that error is not raised and pass if the error is raised. And then now I'll show you the end-to-end test that I wrote. So we want to test the overall behavior, and note that this test requires manual inspection of the results. We want to actually look at the plot and test that it looks like we expect. So this might not be something, this doesn't have any assert statements in it, so it wouldn't be something that the computer could check on its own. So we define our data parameters, we generate some noisy data here, we run our code exactly as a user would. We instantiate this compare fitter object. We then run the fit line method, then the fit quadratic method, and then we plot the best one here. So this is what we get at the end. So that looks pretty good. So I feel good about this overall end-to-end test. So at the very end, I talked about how you might work to improve the original code. And the hint that I gave for this was thinking about how users might break the code and how you could design it to decrease the probability of breakage. And the purpose of this was to show you some of the drawbacks of object-oriented programming. Remember, Jason said on the first day that object-oriented programming depends on the current state. So for example, right now the code breaks if you don't first run fit line and fit quadratic before plot best. And the reason for that is because plot best is, oh, that's my test plot best. Plot best is accessing these self.linear residuals and self.quadratic residuals attributes. So those are actually only defined in these functions. So if you don't run those functions, it's going to give you an error that this attribute doesn't exist. So it depends on the state of the current object. So one thing you could do is you could, define self.quad coefficients as none, or you could raise a descriptive error if the user tries to run this plot best method without first running those other two methods. Another thing that I suggested is it would be good to add a descriptive error message for the empty array case rather than letting the internal NumPy polyfit catch it. This is because often your users won't necessarily know, if you get this NumPy polyfit error, they're not going to be like, oh, that's because I put in an empty array. So having an actual descriptive error message that says, hey, you put in an empty array, this is what you're supposed to do instead, will help users to spend less time debugging. The last thing that I suggested is that if we're running this many times, we might not want to plot every time. So maybe we could add a keyword or to separate out the plotting and numerical comparison functionality into separate methods. Mm-hmm.
More of a code theory question. Would it be bad practice to, within the plot function, force the call to the other two functions, or should we keep those calls entirely separate?
Yeah, that's a great question. So the question was, would it be better practice to, within the plot best function, actually do the calls to the original functions? I think it really depends how you envision users using the code. So maybe I guess you could still keep those other functions and people could just run those other functions, and then within the plot best, you could also run those. You might not want to rerun it, for example. So maybe one thing you could do is check if it's already been run and then rerun it if it hasn't been run. Yeah, I think that's a good suggestion. Yeah. Any other thoughts or questions?
Also, I discovered that the polyfit, so for the line, if you just provide like 2 data points, like 1, the statement breaks because for the line it's completely specified and the residuals are empty. And likewise for the parabola, if you just provide 3, it's also empty, so the statements in the loader break. So I think that if we want to keep that structure, like we'll just put an assertion in the initialization, like, oh, user must provide at least 4 points, or something like that.
Okay, nice, cool. I didn't even know that. So the statement was that if you have not enough data points, so if you have only 2 data points for the linear fit and only 3 data points for the quadratic fit, then the code is going to break too. So we should make sure that we like catch that error explicitly, or that we like provide a descriptive error message in that case. Yeah, awesome. Any other thoughts?
I don't know if this was just me, but the residual, but it would define would be an umpire array, and so I had to add another line which just added up the residual to the output.
Yeah, nice, yeah. So the statement was currently the way that NumPy residuals is defined, it doesn't actually add up all of the residuals. I think the reason that this happened is that the behavior of like comparing NumPy arrays changed somewhat recently. So I think this used to work. You could compare like element-wise, and nowadays you have to include like a numpy.all to make sure that they're all less, or do this sum. So I haven't gone back to this code since I wrote this a couple of years ago. But yeah, awesome, thanks.
I have a random question. Were you able to get the plot to ever say the linear line was better?
Yeah, that's a good question too. That's another sort of Easter egg in this. So the comment was, were you ever able to get the plot to say that the linear line was better? And no, actually, like analytically, the linear line should never be better because you're comparing something with more degrees of freedom to something with fewer degrees of freedom. So the quadratic will always be better. Yeah, nice.
So this, so I assume, so imagine you have a piece of code where the user doesn't provide any input actually, for example, a piece of code that loads a catalog from internet. What kind of tests would you define there?
Yeah, so the question was, if you have a piece of code where the user doesn't provide any inputs, what kind of test would you write there? You still want to test that the code like produces the expected output or produces the expected like state. So you don't have to necessarily then worry about testing for different types of inputs, but you still want to test that, like, if it loads a catalog, for example, that the catalog was loaded and that, you know, for example, the first line of the catalog is what you expect. Yeah, good question. All right, we've been going for a while, so let's take a 5-minute break. We'll return at 42 after, and then we'll continue with the tools for testing, and then last we'll do the anti-discrimination. All right, everybody, let's get started again. So now you've gotten some practice thinking about how to write tests and like what makes a good test. So now I want to spend the rest of the time talking to you about tools for testing. So the clear industry standard for executing tests automatically is a piece of software called PyTest. So it's very simple. Basically, it works that all functions beginning with test underscore are collected and executed. And then failures and warnings are reported to the user. You all actually already have experience with PyTest because this is the utility you use to test Orbitize that it was set up correctly when you were setting up for the workshop. So you've seen this already, but I just want to show you again like how this actually works with your new testing knowledge. So if we're in the Orbitize repository now, let's check where we are. So if we're in GitHub/Orbitize/tests, so our tests are all here at the same level as the root repository. And we've got all of these guys here that start with test underscore. So PyTest will collect everything in these test underscore.py files, all functions that start with test underscore, and it will just execute them. So if you just type py.test, it will collect and run all of those tests. You can also choose to run a subset of the tests. So ignore this UV run that just runs it in this UV environment, but this is the command that you would do in a Conda environment, py.test And then if we're only choosing to run the tests in one file, we just put the name of that file, so test driver. So the first thing it's doing is collecting all of the tests. So it's found 3 tests so far. And then you can see that it gives you a little green dot when everything's passed. So then it says that all the tests were passed. If a test fails, then you get the error there. So this is a really nice way to run all of your unit tests. All right, so I've also talked a little bit about continuous integration a couple times so far. So continuous integration, just to define that term again, is a tool for maintaining your code's behavior over time. So it's a development practice where a suite of tests is run automatically each time a code is changed. So there are a lot of different continuous integration tests. There's continuous integration tools nowadays. There's not like one sort of clear winner the way that PyTest is like the utility that actually like runs the tests. Most of these continuous integration services are built off of PyTest. So you can test that PyTest is working on your own computer, and then you can sync it up to whichever one of these continuous integration tools you use and run that like from GitHub, for example. In general, best practice is that your suite of continuous integration tests should touch as much of your code as possible. So meaning that you want your tests to actually like run, as many lines of your code as possible. And also they should take no more than a few minutes to run. This first point of your suite of tests should touch as much of your code as possible is a little bit of a trap because it's absolutely possible that you have 100% coverage of your code, meaning that every single line of your code is actually touched by your tests, and you still have plenty of bugs in your code. So complete coverage doesn't mean bug-free, and it's okay to not have 100% coverage. You want to have like more than like 10% coverage, but coverage is only important sort of up to a point. You also want to spend time thinking about like, am I actually testing the important use cases of my code? So I'm going to give you a tour of one free continuous integration service that I use for Python packages called GitHub Actions. GitHub Actions is a really powerful framework. It's relatively new. I think I only started using it like 2 or 3 years ago. And basically it's just a way to like trigger anything automatic on GitHub. So anytime it's this framework for like, if something happens to your repository on GitHub, then do these specific things. So you can imagine that's a really helpful framework for writing for unit tests. So let me show you how this works for Orbitize on GitHub. So if we go to Orbitize, on the top here, there's this tab called Actions. So all of these here are different actions that we have set up for Orbitize. So these are things that run under different circumstances. So our continuous integration test suite is here. So you can see when a test passes, these are run for different branches. So anytime someone makes changes to a branch, this test suite is triggered. So like this branch, for example, has been having some issues. So this one actually errored out. But this one the tests have been passing. You can see when the tests fail, rather than like actually experience an error, you get a little X here. So you can actually see, let's go into one that failed. So the continuous integration suite here is run on 3 different versions of Python. I should update this, so it's the latest version of Python. If you click on one of these, you can then see what the test actually did. So let's compress this so you can see it. So the first thing it's doing is actually setting up the virtual environment that it's going to run the tests in. It's installing Orbitize and installing all of its dependencies from scratch. And then it's just going to run PyTest. So you can see once we get in here, it looks exactly the same as PyTest. It collects all of the tests to run, and then it runs all of them. And you can also see which ones failed here. And then at the very bottom, you get this report of which tests failed. Yeah, I think that's all I wanted to show you here. We have other GitHub Actions set up to, for example, test the Jupyter Notebook tutorials. This is a little bit more computationally intensive, so I only run this when somebody is making a pull request to main, not anytime someone makes a commit to a different branch. We also have our docs automatically rebuild every time someone makes a change to main, so that's also here. And yeah, there's a couple others, but I need to talk about them. It's one thing I really like about GitHub Actions is it's relatively easy to set up. You can kind of just click through the prompts. I've got some instructions linked for you in this presentation, I think at the end. Back in the day, we used to have to deal with really annoying continuous integration services, and they were terrible. And I'm very jealous of you that you don't have to do that. All right, I also want to briefly talk about tools to control the environment of your tests and or the environment of your code itself. So one thing you might realize after being in Code Astro is that running the same code on different operating systems in different Python environments can be very frustrating, and there's sort of subtle differences that make themselves known. So you can get around this by actually creating a standardized environment for your code or for your tests. So there are a couple different ways to do this. One really popular method is using Docker. Docker is a tool for deploying applications inside of containers. So basically this is creating a fake operating system inside of your operating system. You can also control what Python packages are installed there, what other types of packages are installed, not even necessarily Python packages. Docker is really popular because it's very lightweight, meaning that the containers don't take up a huge amount of space on your computer. You can also use virtual machines, which are similar, but in addition to emulating different operating systems and software environments, they also emulate different hardware environments. So a virtual machine would enable you to, for example, if you have a Mac, create a virtual machine that emulates a Linux system and test your code in that system. So one service, continuous integration service that uses virtual machines to test your application on different operating systems is AppVeyor. Question?
You say virtual machines can emulate different hardware, but Mac, Windows, Linux, that's software.
Yeah. So the question was virtual machines can emulate different hardware, but Mac, Linux, et cetera, are different software. Yeah. So I guess I was also thinking about Macs will often have different hardware than Linux machines, for example. Yeah.
But then can you emulate different graphic cards, different CPUs, or is that too much to ask for virtual machines?
Yeah, I don't know a ton about them, honestly, but I think so. They basically work by creating virtual memory and stuff. So they're going to behave exactly the way your machine will behave. So they're going to compile your code in exactly the same way that it would be to get to machine code on that individual machine. Yeah.
So from yesterday's class where we had the requirements.txt file, is that kind of similar to the Docker containers that you have to set your environment, your pip install, is that similar or?
Yeah, good question.
What is this difference?
Yeah. So the question is how does requirements.txt, for example, differ from a Docker container or a virtual machine? So I think the requirements.txt is a way to specify that these are packages that you need to install in order to get my package to work. But for example, different computers will have different numbers of bits to represent integers, for example. So that's a thing that for the most part, Python conceals from you. Python figures all that out for you under the hood. But if you're if you want to actually make sure that your implementation, especially if you're working with much lower level functions, if you want to make sure that your implementation works in different computing environments, that's something that a Docker container would do for you.
So is it a way to compare, for example, Docker and virtual machines? You have two different computers, one has Mac and one has a PC, and the requirements.txt is more we both have Macs, we both have a Python, it's an ecosystem and it should work. Is software versus like a hardware kind of?
Yeah.
I think it's all right too.
Yeah, kind of. So the question is like, is requirements.txt more a way of saying like, we both have Macs and I want to, install this, like, this piece of software in both environments, and Docker is more like for Docker virtual machines are more for testing on different hardwares. It's a little bit hard to like sort of understand because Python sort of conceals a lot of this like these details from you. It handles a lot of this stuff for you. So I think in practice, the way that I've used Docker in the past is I want to like create an environment and just like ship it out with the code so that anytime somebody runs the code, I can guarantee that all of these packages are going to be installed. The file system is set up exactly the way that I want. What else? That like if you want to set any like environment variables, for example, you can also do that. So it's like a sort of second level of like control over the setup. So you might imagine like this is really popular when you're like gonna, run a piece of code that needs to be like exactly the same every time. And like you want to make sure that like, yeah. So if you like, for a lot of Python applications like AstroPy, for example, AstroPy wants very explicitly to be able to work on everyone's computer. Like AstroPy doesn't want to, like it wouldn't be in AstroPy's best interest to like, rely on, a particular setup. So like shipping a Docker container out with AstroPy doesn't really make sense. They want to make it easy to set up and very flexible. So it's sort of like different levels of control over the environment that your code is run in. Yeah, great questions, thanks. Any other questions? Mm-hmm.
So I've got some programs in Python that run under Windows.
Mm-hmm.
Windows installation Python, and I want to write some front ends to those. And yet I'm kind of working in Unix, Linux here. And now I'm wondering, would these be applicable to try to kind of cross that boundary?
Mm-hmm. Yeah, so the question was if you have some Python codes that like specifically run in Windows, but then you move to a different operating system or different like hardware system entirely, and you're now working on Linux, would some of these tools be applicable? So definitely, and like virtual machines in particular, like one of the main use cases is like running like pieces of software that like, wouldn't work in other circumstances. So if you have like a sort of legacy piece of code that like requires a specific version of Windows, for example, you can make sure you can like sort of freeze that version of Windows and then distribute that virtual machine to be run on any other computer. Yeah, so that should.
So I could write it in the environment that we're using here, but then if I do it, if I was in this virtual machine with the distribution, then it would work fine.
Yeah, exactly. So yeah, he was saying that if you write the code in Windows and then use the virtual machine, you would be able to use on a different computer. Yeah, it's definitely true. Yeah, so definitely encourage you to look into this for that. Yeah. All right. So here's a really nice like video that I think Daniel suggested about Docker containers versus virtual machines, if you want some more info about like how they work differently. All right, so the next thing I want to do is to just get some best practices from the class about like what are the best practices for testing. This is not a trick question, like definitely feel free to repeat things that I've told you already. But I also want to like benefit from the experience in the room. All of you are also software developers, and you also have a lot of thoughts about testing and great like experience and input. So I want to like collect the wisdom of the class. So I'm going to ask the people on Zoom to use Stack. So the way that works is if you have something to say, you just say Stack, and then I'll call on you and ask you to unmute. And then you can add what you think. All right, so folks in the room, feel free to raise your hand. So what are best practices overall for testing?
Use well-defined variables.
Nice, yeah, use well-defined variables. That's a good like best practice for coding in general. Yeah, using descriptive variables. Yeah, exactly. I'll rephrase this as descriptive variables. Like no test A, test B. Nice. Yeah, great.
Don't use print statements.
Yeah, nice. So you want to make sure your tests actually like fail or pass. Yeah. So don't use print statements. Make sure tests either pass or fail. Nice.
Always have in mind the trivial cases of your code.
The trivial cases you said?
Yeah, the trivial cases.
Yeah. So always test trivial cases of your code. Exactly. Yeah. And this is a really good like point for maintaining behavior over time. So even if it seems obvious to you when you're writing the code that like, oh, of course it's going to work for this thing, like maybe it won't actually work that way in the future. So having that test there is one really easy way to help you check. Unit tests can also, I don't think I really mentioned this yet, but like if any of your dependencies change behaviors, like having descriptive unit tests that will fail is really nice. And having this continuous integration setup can help you catch that very quickly. Other suggestions?
Type hinting.
Sorry?
Type hinting.
Type hinting. Yeah. So this is interesting. So we were just talking about type hinting yesterday, actually. So type hinting is this practice where you put the type of the variable inside the function definition. So like my test, it takes an integer, and then you can say that this is type int. And then you also assert that the output is of type int, for example. So this is nice because the Python test will fail if you don't actually use these types of inputs. I think my sort of hot take about type hinting is that you can end up with these like super long like descriptions of what the actual inputs and outputs are, and it can get kind of like messy and difficult to maintain. So I think I tend to like type hinting in specific cases, like when you have when you really need the input to be a specific type. I think it's a really good use case because you want the test to fail if somebody doesn't put in an integer, for example. Yeah. So this was a good way for me to have my rant about type hinting. So let's say type hinting, also called strong typing, can be helpful for asserting certain input/output types. Nice. Let's get a couple more.
I have a question about type hinting. If you pass a float and it's like, if it's a Python float or a NumPy float, or maybe there are other types of floats, how will that be handled?
Yeah, good question. So the question is, if you like assert that the input is a float and there's like different types of floats, NumPy floats versus Python floats, how will that be handled? I don't actually know. Does anybody know? I think I just have to test it out. Yeah. Good question. Other best practices for testing?
Something else to add on the trivial, like testing the edge and boundary cases.
Yeah, absolutely. Yeah, testing edge cases and boundary cases. Excellent. Yep.
It's kind of similar, but if like other people are going to use your code, maybe try to consider like they don't know anything about computers or anything, account for user error.
Yeah, totally. Yeah, so account for user error. Yeah, this is really good. So I said earlier that you don't need to test inputs that are not allowed by your documentation. However, if you anticipate that users are going to make a common error, it's really nice to like raise a particular, like an informative error that says like, you know, hey, like I know you put in this error because you thought this code functioned this way, but it doesn't actually function this way, and here's what you should do instead. So that's another like good best practice for writing usable software in general. Yeah, awesome, great. Mm-hmm.
Probably test as you develop, not just stay with the last step.
Yeah, excellent. So test as you develop. Yeah. This is a really excellent suggestion. And I think I'm going to talk more about this in a couple slides, so I'll leave it for now. Maybe one or two more thoughts from folks in the room or folks on Zoom? Mm-hmm.
Restart your kernel before you test.
Restart your kernel before you test. Yeah, so this is a like Jupyter notebooks are going to be sensitive to the current state of your environment type thing. So I think maybe this is sort of related to another best practice, which is to test like outside of Jupyter notebooks in addition to like writing tutorials in Jupyter notebooks. So in Orbitize, we end up doing both. We have some Jupyter notebooks that are the tutorials, and we do like test that those run all the way through, for example. But our like suite of continuous integration, well, our suite of unit tests is all like purely functional. Yeah. So I'll rephrase that too as like tests should be functional as much as possible. Yeah, not rely on the state, on current state. Awesome. Okay, great. These were really great. These are all very creative. Thanks, everyone. So here are the the general like summary that I came up with. So test as many use cases of your code as possible, writing both unit test and end-to-end tests, writing tests throughout the development process. Many developers advocate for writing tests before you write code. So this is called test-driven development. So you figure out exactly what your code's outputs are going to be for given inputs. I don't usually do that, to be honest, but I do this like sort of hybrid approach of like writing tests as I'm writing the code and then going back afterward and writing additional tests. Another good practice is to turn debugging scripts into tests. So especially when your users start contributing bugs that they found, if you end up writing a script to reproduce that bug and then you use that script to debug it, take that that script that you wrote and then put it into your suite of continuous integration tests. I also talked briefly about coverage. This is just like the number of lines of code your tests touch. So coverage is important up to a point. It's more important to test your code in all the ways your users will apply it than to worry about getting 100% test coverage. 100% coverage doesn't mean bug-free. And then in general, another piece of advice that I often give when someone says they want to like get started working on a new piece of code is to write tests for the code. So this is a very like win-win situation. If you like write to a developer and say like, hey, can I write some new unit tests for your code? They're going to be like, oh my God, yes, please, thank you. And as you like figured out with the linear quadratic fitter situation, this will help you like get to know the code very quickly. All right, so now the next activity is just to write unit tests and end-to-end tests for your package. So I'm going to give you, I think, 15 minutes now, and then you'll have time later this afternoon, of course, to continue working on your package's test suite. So we encourage you to write your tests using the PyTest framework, and you can actually run PyTest on your test suite in order to test that your tests are passing. The output of this is to push the code for your test to your group's GitHub repository. And then if you finish early, you can also get GitHub Actions continuous integration set up for your package's test suite. And there's some instructions at this link here about how to do this. You can also, if you are feeling inspired, learn more about Docker and get your package set up to run inside of a container. And I've got an example implementation for you to check out for reference there. Okay, so you're not going to get all this done in 15 minutes. This is basically just to like give you a little bit of time to get started. And then we'll do our anti-discrimination lesson, and then we'll go to lunch. All right, everybody. So we're going to take a 5-minute break now. Remember, you have all afternoon to keep working on your tests and pip installs and documentation, everything like that. And then we'll do our last lesson of the mandatory morning lessons, the anti-discrimination, starting at 30 minutes after the hour, 11:30 here. All right.
Okay, everyone, let's get back started. This is our
Sorry.
this is our final lesson for the synchronous part of Code Astro. So we're going to talk a little bit about anti-discriminatory practices in software development. So a couple disclaimers to start off with. We'll try to make this somewhat general, but your instructors are all kind of based in the U.S., so it's a little bit U.S. centric, but hopefully many of these can apply broadly as well. We start off, I just want to acknowledge, software engineering can and does contribute to discrimination in different forms. And one of the parts of this is always important to reflect and assess on how we're developing code and how we can be doing better. Before we dive straight into software related things, just kind of to contextualize everything, I want to just talk a little bit about bias. There's kind of two kinds of bias or discrimination. One is kind of explicit or conscious bias. This is where discriminatory action is intentional, clear, and overt. And then there's also implicit bias or unconscious bias, where a discriminatory action is unintentional. Oftentimes, the person doing it is even potentially unaware of it happening. And many things, there's things happening that are in the first one. There's also many things happening that are also in the second one. And this is where bringing awareness and talking about this and going over this is an important thing, so that we can identify, especially these second cases, and try to mitigate these, as well as understanding when the first cases are happening and try to combat those as well. So there's kind of many ways that's kind of happening. We have kind of discrimination in the field of software engineering. One is just, who is a software developer. So on the bottom here, these are plots of the Google workforce representation in 2024. You can see that basically the split in both between men and women, and also a split based on ethnicity in the U.S. offices. These are all U.S. offices and U.S. statistics. Note that there's been no similar statistics published in 2025 and 2026. Google stopped reporting diversity-related hiring goals in the last couple of years. So part of why this is happening is that the hiring that's done in software engineering, there's oftentimes discrimination kind of hidden, or kind of sometimes implicit, sometimes explicit, especially this idea of what's called a quote-unquote cultural fit, hiring people who are the most similar to you, that you identify the closest with, that maybe share the same culture, the same backgrounds and things like that, that kind of reinforces discrimination. And this, if you already have some sort of inequity, it just kind of is a positive feedback loop on top of that. There's also been in this slide, which you can find in the day 4 folder, all these little underlying things. These are all links. So we try to do our own research. This is kind of accumulated throughout the year, some of which might be like older stuff from maybe 5 or 6 years ago, but you can click on these and read about and learn more about these yourself, because we aren't going to go over every one of these specific details in particular. But there's been quite extensive kind of documentation of how culture fit has been led to kind of inequitable hiring in tech companies, both especially as a function of ethnicity and as also a function of gender. This is kind of actually, but despite like this, even this is happening even though that, there's also been studies that have shown that kind of more diverse companies in general perform better compared to companies of the same kind of stature and, in the same field that are less diverse. So increasing diversity has been shown to basically allow companies to have higher performance. And, despite this, these kind of trends are still happening in the hiring in software. Software itself is also not biased, not unbiased. Sometimes there's this argument that like all these algorithms are just math, right? How can math be biased and things like that? And a lot of the issue here is the underlying kind of context in which this math is being operated on. So on the bottom left, this is a recent study on large language models, and like if you give a large language model a list of references with clearly male or female author names or author names from majority or minority groups, how often are they going to cite those authors? And there's basically shown to be a preference for men and people from majority groups, whatever the majority group is in the context in which you give the references. This also happens with search algorithms or LLMs. You ask it to, here in the bottom right, this is an image also from a study where they asked some AI image generator to create a book cover with the main character of a fantasy book for 14-year-old girls, and there was nothing here specifying the race, what kind of what kind of what kind of vibe or setting that this is being done in, but this is this is the kind of image that these produce. And this is a lot of this and happens because these algorithms, although they're just numbers, right? They operate in a context in which there is discrimination, there is bias already implicitly throughout our world, throughout in the data, in the training sets that these algorithms use. One example of this is, there's these companies that sell their services to local police agencies, trying to predict where crimes would happen, so that they would station more officers there to kind of prevent those crimes. But there's been a history, especially in the U.S., of kind of discriminatory policing, where they preferentially police in areas that are maybe majority black or majority brown, and that leads to more arrests, which then the algorithm learns that these are places where crime is happening, so then we station more officers there, which leads to more arrests, and then this creates this positive feedback loop of this kind of discriminatory policing. So these are all things where in which software, the math is math, but in the context in which it operates, still can produce biased results. There's also been we can also correct for biases. This is a history of Code Astro. We've talked about kind of AI generated things and biases in it for 7 years now, and we keep updating the slides, but this is like a snapshot of what we showed in the past. Back in 2022, when these generative AI things just started becoming popular, you can create little AI art with some sort of prompts. We had this one, look, you can make astronomers at a conference, and and you can see the lack of diversity perhaps in the images generated. They generate predominantly white men and telescopes as the main attendees of astronomy conferences. And then people were like, oh, we can just force our AI algorithms to always construct a diverse sample. But then there's subtleties in this, right? If you ask the AI, I want to generate pictures of historically accurate U.S. senators from the 1800s, that you're not aiming to get diversity in your pictures there, right? This is something where it's not just like a single kind of naive fix can solve it. It requires resources, requires kind of subtlety, requires experts, and requires kind of these companies or people who are building these models to invest the time. And these are not unsolvable problems. You might notice that these images generally are getting better and better and better because people are investing some money and resources in trying to make them better. So this is stuff that we can solve if we want to put our time and resources into. Software, again, doesn't live in a vacuum. Even if we just make tools, the tools we make can also be used in various ways, especially with these generative AI things, these deep fake kind of videos and things like that have become more and more prevalent. Basically, deepfake videos are basically taking prominent individuals and making them say things that they didn't actually say, but because there's so much training data of how they speak, their mannerisms, their voices, you can generate kind of things. This has been done for fake news, has been done in Hollywood for movies, for people that have passed away, and this has been now shown to be used widely nowadays to kind of promote kind of discriminatory or violent actions, basically producing content that's not real but kind of makes the people who consume it, have some sorts of tendencies or calls to potential action in nefarious ways. This software also can affect it is also a question of like when you're using it and the data you produce, who's benefiting from that data. So when coming a little bit closer to like software development itself, LLMs like Google GitHub Copilot can be used to produce code, and we talked about vibe coding. And they're trained on large amounts of both public and private data. So they oftentimes don't disclose, but generally it's assumed that they're also like, GitHub has access to all your private repos that are hiding that normally people in the public can't access, but GitHub themselves can access it fine, right? So there's and it's been shown that in the past, and maybe it has changed now, this was like 2 years ago, 1% of Copilot outputs have snippets of code like greater than 150 characters that match exactly the training data. So you're able to basically use this tool and basically take data that other people have written basically and take it from them. And then there's also a question of whose data is it and who's earning money from that data. So it's not only a question of like maybe intellectual property, right? But it's also a question of data ownership and also who's profiting from this data that is being harnessed. I think this is new from this year, but with now the explosion in data centers being built out, there's the build out of data centers to support all these new computing algorithms, especially these generative AI algorithms, has been putting a stress on local resources like water and electricity. It causes pollution, both regular pollution, air pollution, and noise pollution. Also thinking about land use and who controls land use and who should be deciding how to use this land. And those are all kind of general issues. They're not they're all on themselves potential things we want to mitigate, but they're not potentially at face value discriminatory, right? They're just issues with AI build out, and the vibe coding lesson has a bunch of links to those issues. But then it comes to a question of not only are they causing these issues, but then these data centers are now, where are they predominantly being built? A particularly rich, affluent community maybe has a much better ability to block the building of data centers. Whereas we're seeing right now that data centers are particularly impacting rural communities, their infrastructure, and their land use. And the effect of that. We're also seeing data centers being built in low income and marginalized communities where folks either don't have as strong of a voice or don't feel like they have as strong of a voice, so they don't engage as much with maybe say local government and don't prevent these data centers from being built in perhaps their backyards. Mississippi and Memphis, Tennessee are two examples of this. You can click those links. The picture on the right is from Memphis, Tennessee. This is a XAI data center that was built there. They didn't have enough power from the local grid, so they brought in like 30 portable gas generators to power the data center. And those portable gas generators are basically extremely, they're basically polluting the local area and has led to a bunch of health issues in the local community, which is predominantly Black and low income. And you can read a bit more about that in one of the links there about these effects. This also brings us to environmental considerations. There's also inherently there's environmental considerations. This is not about AI. This is actually about astronomers. So these are actually studies conducted by astronomers of the CO2 footprint of typical astronomers. This is one done in Australia and one done in the Netherlands. The units are this like tons of CO2 per year. It's a little bit confusing on the left plot. This is done per person. On the right plot is done per institute. So the numbers are a little hard to compare, but I want to draw you to the supercomputing bar. The supercomputing bar is how much computing time people are using for astronomy tests. It's like you running your simulations, running your data analysis scripts, all those things. You can see for in Australia, they're averaging like 22 tons of CO2 emission per year per astronomer. For context, a typical U.S. Household emits about 7 tons of CO2 per year. But this actually depends quite a bit. If you look in the Netherlands, if you look this here in the supercomputing at Leiden, they're using about 53 tons of CO2 per year per institute. And in that institute, there's about 320 research staff, so it's actually less than 1 ton per year per person. And this is about what kind of energy use is powering these supercomputing centers. Australia has a large number of coal power plants, whereas the Netherlands has mainly been using things like geothermal and other low carbon emission power to power their local power, local supercomputers. So what kinds of power are being used also affects the CO2 footprint. But the CO2 footprint again is just the CO2 footprint. But then we have to think about putting CO2 in the atmosphere. Who is benefiting from the computation time? What kinds of nations, what kind of people are benefiting from these computation time, and who is impacted by climate change the most? Generally those from poorer countries, those have less means and resources are less able to adapt to the changing climate, whereas those from more affluent countries are able to get the right resource, get specific resources to adapt to, say, heat waves are happening and things like that. And now, just new for this year, AI has been, now barged on the scene as a very large consumer of energy. And one of the challenges of AI, one is its inherent energy use, but the other is that these AI companies right now are kind of purposely obfuscating their token and energy use. So like you try to look up, how many tokens you've used, or and things like that. It's actually really hard to find, and you oftentimes have to kind of approximate these things. And there's actually people that have done those studies and tried to approximate the energy used and things like that. But there's maybe like purposely to try to make you not think about what kind of energy use is happening with the computing power you're doing. And then lastly is also about access to AI tools. This is happening especially in the last few months, as these models get more and more sophisticated. We're starting to see these models no longer being open, that anyone in the community can use them. Anthropic, with their latest models of Claude, are choosing which countries and which individual persons even get access to the latest AI model. So there's an unequal distribution of who has access to this technology and who can do what, and who are the people in power that control that. And as these models are becoming more and more expensive and less subsidized, who can even afford to run these models and things? And so I think questions of access and availability and that inherent kind of discrimination that brings about will become more and more of an issue in the next year as we talk about this more and more, I think. So this is kind of a broader picture of the state of software development and how various things are affecting software development. This is kind of like the first half of this kind of lesson, and the second half we're going to transition more to like, let's think about. Oh wait, there's one more actually. We talked about a lot of bad things, and things that maybe we don't want to have, but these the new improvements in technology and new tools, do clearly provide some, clear and tangible benefits to the world and to how we can develop things, making things more accessible, making lower barriers of entry in various fields and things like that. But I think this is now our personal opinions. Clearly regulation is needed. But legislation historically has been shown to be slow compared to the process of development, so it's always in some sort of catch-up space. So some things we can do to try to balance utility and harm. We can try to be judicious on how we use these tools and what they produce. Trying to be careful in prompting and analyze AI outputs to avoid things like hallucinations and made-up references, things like that. And also, think about only using these AI tools as needed. Like what in which cases are is actually helpful to me, or in which cases can I use something simpler and still get the same results without having to use these AI tools. And also maybe limiting the use of what's called quote unquote agentic AI. Agentic AI is basically AI. You might have heard of it. It's like AI. This does more than just like you give it a chat prompt, gives you an answer. It's more like you give it a chat prompt, and then it like talks to itself multiple times to try to reason what are the next steps to do, and basically try to do a higher level task. It's not like there's no like exact definition, but basically trying to do a higher level task than just like one chat prompt, one response. But these agentic AI tools generally use orders of magnitude more tokens, which use orders of magnitude more energy and other resources in order for these things to happen. So thinking about when to use agentic AI and think about when maybe we don't need to use agentic AI. We can also teach others about these issues, especially with things like implicit biases. Awareness is kind of the first step to kind of mitigating and catching those things. And just being in general, knowing about these things and knowing what the relevant issues are and staying informed. And then lastly, we can always advocate for more oversight. It's not like, it feels like sometimes AI is the Wild West and technology is the Wild West, but oversight is happening. A couple years ago, Google and other AI companies like Facebook allow basically acquiesce to EU AI regulations that basically put rules for how people can choose to opt out of the training data for AI. They put rules on forcing these companies to disclose, at least on a high level summary, what their training data is. So not exactly publishing every single piece of training data, but where they got their training data from. And also banning the use of blanket facial recognition usage in public. So not just like having a camera that just looks at everyone and checks everyone's pictures all the time, only when it's allowed for specific cases. So this is an example of success, and I would say success in being able to regulate some of these things, maybe potentially without trying to limit, like preventing technology from growing, right? It's a balance between allowing technology to grow and also trying to limit harm of the new technology. Okay, so this is kind of more global pictures about the world of software development and technology and AI nowadays. I want to then now shift to kind of thinking about like how we develop code as like astronomers and as small groups and teams as we are building our code bases. So, you can do your part in not contributing to an exclusionary culture. We talked about this in the very beginning, the first day of kind of like kind of rules of discourse and things like that. We don't advocate. We advocate against language hate. So, don't tell people like, I can't believe you're still using IDL for that. Things like that. Whatever people are using to get something done, it's a perfectly valid way, right, for them to do science, right? As long as it works. So we shouldn't single people out for you maybe not using the tool that you find that you prefer. Don't micromanage other people's code. Like, if as long as it's working fine and not raising problems, it's like, oh, you should be using iterators to do that because it's much simpler and quicker, things like that. But if any other piece of code does the job and gets things done and doesn't create other issues, I think, let them do what they like, let it be. Don't minimize what other people are doing. Things like, oh, it's trivial to set up all these set up the content environment on WSL, things like that. Be transparent when kind of hiring, recruiting, or contributing to code. Don't judge other people's coding environments and how they're set up. And I'll have a growth mindset. Not everyone knows everything, but they can learn it. So just because they're maybe not at the level of Git that you are, but you can bring them there. Valuing a diversity in skill sets. Not everyone needs to know everything. But they also bring probably other skills and other expertise that are valuable that maybe you don't have as well, and being able to recognize that complement of expertise. And also giving credit where credit is due. That's always been an issue in history that has led to various kind of discrimination in who is recognized in science. kind of going down to even more specifics of how we code. There's we want to replace discriminatory language in coding. Some sorts of discriminating language is the use of things like master and slave when we're talking about maybe like one copy of something that's like the primary copy and another copy that's kind of like the backup copy of something. There's generally for these kind of discriminatory language, is usually much better in terms of accuracy and clarity of language than the kind of original language that's been historically used. Things like primary, backup, leader, follower, writer, reader, main, helper are much more clear and like direct on the purpose rather than the original master slave. Similar thing with blacklist and whitelist. You can use block and allow. The master branch on GitHub has this weird whole etymology that you can read about if you are interested. That's why in general nowadays we always talk about the main branch as the main branch, which again makes more sense because it's the main branch. There's also cases specific to astronomy. There's this package called Source Extractor that the developer of Source Extractor chooses to abbreviate in a very particular way, and you can choose not to do that. You don't have to follow their choice. And in general, this falls under a broader category of using descriptive and professional variable names. One of my personal pet peeves is the use of don't use swear words in your code, even if you're very frustrated about why the code is not working. Code is the face of your software. In astronomy, if you're releasing open source code, like the first thing how people are gonna interact with you and know about you if you're releasing open source code is they're gonna look at your code and read your code. So if your code, if that's not something you want to be seen as to be known by, don't do that. Bad variable names such as swear words, make other people feel uncomfortable, and just clear variable names in general just makes your code easier to understand. I didn't put very, very bad variable names as the examples, but you can imagine much worse ones there. But you can always variable names are free nowadays. You can name them as long as you want. It's okay. It can be like a whole sentence. You can use things like temp, image, curve, val. And if you really don't want to name something, the Python standard for an unused variable name is underscore. So just name it underscore if you really don't care about it. Name it underscore. When you're working in groups with other people in software collaborations, definitely you want to, if you're using code from other people, cite and offer authorship to them. You want to pay attention to whose ideas get noticed and credited in the development of the code, because sometimes these things are very dynamic, and maybe one person's advice gets kind of recycled and gets said by someone else, but trying to remember, who was the original originator of these ideas. You want to maintain an open and respectful communication with your team members, treating them with respect, and recognizing the diversity of people on your team and the diversity of skill sets. One of the kind of a corollary to that is kind of to value collaboration over being absolutely perfectly correct. It's more important that you have your team and they work well rather than that you're technically 100% correct instead of 99.999% correct. Iteration is important. These are things that we aspire to. We're not saying we're doing it right. We're not saying that there's any person you can look at that's absolutely doing these things with 100% accuracy, right? But seek feedback on your processes, norms, and codes, and always have this growth mindset to always try to improve. There's many lessons in history of this. One of which is the uncredited women who made the computations that made the discovery of chaos theory. This idea, butterfly flaps its wings on one hand of the world and you get a hurricane in the other several weeks later, kind of thing. This was there were many women involved in the computations that led to that discovery, but because they weren't credited or offered authorship, we didn't know about them until many decades later. If you notice discriminatory behavior in software development, there are things you can do. You can try to, first, for some things, redirect it into a constructive action instead. You try to change the attitude of the person who maybe is doing something, especially on for kind of implicit bias or unconscious kind of activities. Like, oh, can you make your variable name more descriptive? You know, if you find a name that you don't find uncomfortable. If you're familiar with how to do this, could you provide a code snippet to help us get started? If someone's like, oh, it's trivial to do this thing, you should know how to do this or something like that. It's important to call out discriminatory actions. Again, there's many kind of implicit biases happening, and calling them out, because oftentimes the person who did it maybe has good intentions but is unaware. So bringing those out into the forefront is important, especially if you're not from a marginalized group and you aren't the person that those remarks are being targeted to, you know, as a bystander. When you're developing pieces of code with maybe anticipating multiple people working on it together, you can write a code of conduct for how to contribute to a software package. In these code of conducts, usually it's stated what explicitly is allowed or not allowed in the development of this code and how people work together in the development of this code. There usually is stated some sort of consequences for violation of the code of conduct. And if you are interested in code of conducts, there's a link here to the Orbitize community agreement, which is and there's also the Code Astro community agreement that Sarah showed in the first day, which is tangentially somewhat based off of the Orbitize one. So you can read either one of them for inspiration if you are looking for somewhere to get started. If worse comes to worse, discriminatory behavior in software development can be treated like any other sort of professional discriminatory behavior. And we have resources in place to help try to mitigate and handle these incidents, albeit sometimes imperfect. So these are just some of the summaries. I think we said all of these. This was just like a if you felt like this is just like condensed what I just said in the last few slides into one slide. I think this is the end. How are we on time?
Exactly 12.
All right. And that's the end, I guess, of the synchronous activities. Just a reminder, we have 2 optional activities this afternoon. One is a lesson at 4 on profiling, and one is a little bit different, but it's we want your feedback on what kind of future skills you want to see, and this has the potential to shape what Code Astro might become in the future, because we're still working on what Code Astro might look like in the future years, and this kind of 2 o'clock, this focus group thing will be kind of one of these things that might help shape what will Code Astro be in the future years. So hopefully some of you can attend that. Otherwise, let's break for lunch. And thanks for everyone on remote on Zoom for hanging around as well.